Okay, let's get started. So last time we were discussing random experiments, events, right? So today is the time to formalize our concept of a sigma algebra. So remember that last time we were discussing collections of events, right? Usually the power set, the set of all subsets of the random, the sample space is too big for our purposes in probability theory. So we need to restrict ourselves to a collection of the power set, a sub-collection of the power set. So let's say we are starting with some collection of subsets, some collection of events. What properties does this collection should satisfy? What properties should this collection satisfy? So last time we said, okay, the sample space should always be a member of this collection, and also the empty set. And with this logic, we said, if there is an event in the collection, its complement should always be a part of the collection, because it's simply a statement and its negative. Right? So a statement and its negative should appear together in the list of important events. And finally, we also said that if we have two interesting events in our list, we should be able to connect them with and, or, etc. Right? So this motivates the following definition. So it's going to be the definition of sigma algebra. So let's say we have a non-empty set, and always consider this as our sample space in a random experiment. And a collection F of subsets of omega is said to be a sigma algebra on omega if it satisfies the following properties. So number one, as you remember, omega is in F. Number two is that F is closed under complements. So this means A in F implies a complement, which is omega minus A, is in F. So there is a statement and the negative of the statement. And the last one, I'm going to state it for countably many events, although last time in our motivating discussion, we only talked about 2 events. So that's the extension of the idea of bringing together events or statements using OR. So F is closed under countable unions. So this means the following. If A1, A2, etc., meaning that I have countably infinitely many sets, A1, A2, A3, etc., etc., they are indexed by naturals in F, then their union is in F. Their union is in F. And in this case, we call it the pair omega F is called a measurable space. So in this case, omega F is called measurable space. So this is the simplest structure we're going to have in this course throughout the semester. Okay? There's going to be a third component. Do you guess what this component should be? So you have sample space, you have events. What should be next? Probability, right? We're going to add it later, not today. today we will just try to understand how to deal with sigma algebras, okay? Because those sigma algebras are huge collections of events. And let me also squeeze one more term. So if G is a sigma algebra on omega with G being a subcollection of F, then G is called a subsigma algebra of F. We're going to need this term later, but I just want to provide it now. Okay, so this is a definition, and it certainly provides the properties that we talked about in our motivating discussion last time. But for instance, I did not list omega is in F. Omega is in F because I can deduce it using property 2 and 1 together, right? Because empty set is simply the complement of the sample space. So if I use 1 and 2 together, I can prove that omega, the empty set is also in a sigma algebra. So there are such properties. For instance, here I list countably many events, infinitely many events. But what if I have only finitely many events? What if I stop at number 5? Can I still say that just using those 3 properties, can I still say that A1 union A2 union A3 is an element of F? Well, the answer should be yes, so we have to prove it. Okay? So this is the definition, and right now we're going to prove some simple properties of sigma algebras. Just the definition has to be kind of minimal, right? Okay, so now is this proposition. So let omega F be a measurable space. And now we're going to list some properties. So number 1, or let's say A, is that omega, the empty set is in F. And I don't want to list all the properties and then prove them one by one. I just want to prove them one by one now, okay, before listing any other properties. So here's the proof. Well, as I just said, we can just use 1 and 2, right? We know that omega is in F, and we know that it's closed under complements. So if I have omega, I should also have the complement of omega, which is the empty set. So omega, the empty set is the complement of omega, right? And this must be in F, since omega is in F by property 1, and F is closed under complements by 2. Okay. Now, finitely many events. So can I replace the infinite version here with countably many events? So let's state it first. F is closed under finite unions, meaning that if A1 to AN are in F, with n being a finite number, then the union of AIs from 1 to n is in F. How should we prove it? Yes?
We can consider infinitely many empty sets after that index, then apply the third one.
So if I have only 5 sets, well, I can easily extend it to infinitely many sets by saying, hey, let A6 be the empty set, which is in the sigma algebra by part A. Okay? So we're not just using the definition, but we're also using part A of the proposition. So here's the proof. Well, let A n plus 1, n plus 2, etc., be the empty set, which is in the sigma algebra by A. So now we have A1, A2 up to AN already in the sigma algebra. This is given to me. And now I created extra events that are also in the sigma algebra. So they are all part of the sigma algebra. And by 3, we can say that their union is in the sigma algebra as well. By 3, we have all, let me write it this way, the union of all AIs, which is equal to the union of AIs from 1 to n, because the rest are empty sets. They don't contribute anything to the union, so this must be in F. Is that clear? Any questions? So we're using part A, we're using part 3 of the definition. Well, we haven't talked about intersections yet, so let's list a property about intersections. Maybe countably many intersections. So F is closed under countable intersections, meaning that if I have A1, A2, and so on, I don't stop in F, then their intersection is in the sigma algebra. Okay. Now, how should we argue? I know that the union of AIs, or union of sets in F, is also in F. So how can I argue about the intersection of sets? Countably many sets, of course. So if I knew that the complement of this intersection is an F, can I conclude that this itself is an F? Yes, by number 2, right? So what's the complement of this intersection? So the complement of, let me write it this way. The complement of this is what? Union of complements. I guess this is called De Morgan's law or something like that, right? In elementary set theory. So now let's argue that this is in F. First of all, AI is in F. So AI complement is in F by 2. And now I have sets in F, so their countable union is in F. This is by 3. And to finish, I should say that by 2, this is in F, because its complement is in F. So a set is the complement of its complement. That's why. Of course, you can write down the finite version of it. which I'm not going to prove. So F is closed under finite intersections. So if A1 to AN are in F, with n being a finite number, then their intersection is in F. So F is closed under set differences. So if I have A and B in F, then A minus B set difference is in F. And also, since I say it, I can switch the roles of A and B and say that B minus A is also in F. And finally, there is one other type of difference between sets. So if you look at the set difference, it's not symmetric, right? A minus B and B minus A are not the same thing. But there is a similar operation which is symmetric. And it's called a symmetric difference. So let me say this. F is closed under symmetric differences. Meaning that if A and B are in F, then A triangle B, which is A minus B union B minus A, is in F. So just on a picture, this is what I'm talking about. I have A, B, this is A minus B, this is B minus A, and together they form A symmetric difference B. And as a result of the definition and those properties, you can prove that if A and B are in your sigma algebra, in your list of interesting events, then the symmetric difference must also be in the sigma algebra. Okay? So I'm not going to prove D, E, F. So these are exercises. Prove D, E, F. Okay? Okay. So I said at the beginning, well, F is typically smaller than the power set, okay? But of course, the power set itself is a sigma algebra. I mean, what can go wrong, right? The power set is the collection of all subsets of omega. So there is nothing wrong about satisfying those three properties. Everything is in the sigma algebra. Everything is in the power set. So nothing is wrong. Therefore, if you have just a non-empty set, you know that the power set is the greatest, is the largest sigma algebra, biggest sigma algebra on omega. Every sigma algebra is a sub-sigma algebra of the power set, in other words. And it's called the discrete sigma algebra. Discrete sigma algebra. By the way, we also say that the elements of a sigma algebra are measurable sets. Let me say it somewhere. Let me say it somewhere. Remark. If omega F is a measurable space, each element of F is called a measurable set. Measurable or F measurable set. Okay? So this means in the discrete sigma algebra, all sets are measurable. There is the opposite extreme where we have the smallest sigma algebra. And it is sometimes called the trivial sigma algebra. What is that? What is the smallest possible sigma algebra can you think of? So can it be the empty collection? Nothing in it? No. Why?
We should also have the sample space.
Sample space. At least we have the sample space. What else? Look at the proposition, empty set, right? So if I have my empty set and my sample space, would that be enough to qualify for a sigma algebra? Yeah. Let's check. Number 1, easy. Number 2, closed under complements. Well, the complement of empty set is omega. The complement of omega is empty set, so we're done. Closed under countable unions. Well, I don't even have countable unions, so all I can do is to repeat either omega or the empty set infinitely many times, or both. And the union will always be either the empty set or omega. So we're done. 1, 2, 3, always satisfied. So the question is, do we have anything in between? How about sigma algebras in between these two? That's our next goal. So just as an example, let's say we have a picture like this. We have an omega and we have a set A. Okay? So we have omega and we have a strict subset of omega that is not equal to the empty set. So I want my A to be different from the empty set as well as different from the full set, so that this part is non-empty and this part is non-empty. Okay? Let's create a sigma algebra containing A. Well, since I'm trying to create a sigma algebra, for sure these two guys will be in it. So I just start with these two. Now I add A. Okay? What else should I add? A complement, for sure. And I can add many more stuff, many more sets. But let's say I stop here. Is this a sigma algebra? Well, you have the empty set, the full set, A, and its complement. And all you have to do is to convince yourselves that number 3 in the definition is satisfied. And just try. I mean, you cannot go beyond those 4 sets, right? Any type of union that you're trying to create will end up being one of those 4 sets. So this is a sigma algebra. So this is something in between. Another example. Now I want 2 sets, okay, with non-empty intersection. So all those 1, 2, 3, 4 parts of omega are non-empty. That's what I want. Okay, so omega is non-empty. A, B are strict subsets of omega that are non-empty. So let me say are strict non-empty subsets of omega. And what else? Well, A intersection B is non-empty. A difference B is non-empty. So all those things are non-empty. And A union B is not equal to omega. So I want all those 4 regions being non-empty. So now I'd like to have a sigma algebra that contains A and B. So can we come up with a sigma algebra containing A, B? Well, it's going to be a sigma algebra, so let's start with the easiest stuff. And let me also cheat from the previous example. A is here, so is A complement. B is here, so is B complement. Now what else? Now what else? We're playing a game now, right? So we have to use 1, 2, 3, and also, if you like, the properties in the proposition to list other sets that must be in a sigma algebra, if we know that A and B are in the sigma algebra. So what are these other sets? A union B, exactly. Okay. Complement of A union B, which is A complement intersection B complement, right? De Morgan. Well, if I can have A union B, I can also have A union B complement, for instance. And so is its complement. I can do A complement union B. So the complement of this is A intersection B complement. And finally, I can do two complements. And their intersection is A, its complement is A intersection B. So let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Do we have more? Do we have more? Can you take the union of two sets in this list so far and get a different set? Where is A minus B? Is A minus B there? Where? A intersection B complement. Okay, so A minus B is there, B minus A is there. How about their union? Is it there? Is the symmetric difference there? Did you find it? Nobody could find it. So it's not there. Let's add it. And since I add this, I should add its complement and make sure that I haven't listed the complement yet. What is the complement? Well, complement is this and this, right? This and this. A intersection B union, the complement of A union B, which is this. So the union of this guy and this guy. The union of this and this. Just try to rewrite it. You're not going to get a simpler thing. You're not going to get a simpler answer. It's not one of those sets. Just convince yourselves that. Just work on this picture, okay? Find out which part of the picture corresponds to which set, and convince yourselves that this is not one of those previously listed sets. So now we're done. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 sets. Indeed, there are 16 sets in the sigma algebra. So this is kind of a minimal sigma algebra, right? So if you want to have A and B for sure, this is the minimum that you have to include in your sigma algebra. If you want other sets like C, D, E, it's fine. You can add them, and it's going to make the collection even larger. But if all you want is to have A and B, this is your minimum. Okay? Maybe I should say, come up with a minimal, smallest sigma algebra. So the philosophical point about this is the following. If you remember from last lecture, we talked about events and their meanings. So events are like yes-no type questions, okay? What type of questions do you want to be able to be do you want to be able to answer? What type of yes-no type questions are you interested in? Okay? So every single event is like a yes-no type question, and once the experiment is performed, you are able to answer this question, for sure. Because you know the outcome, and you can check, you can test if your outcome is in A or not. If it's in A, this means the event has occurred, otherwise it did not occur. So, the thing is that if I'm interested in two questions A and B, two yes-no type of questions A and B, and if once the experiment is performed, people tell me the answers of those questions, these are the other questions that I'm able to answer. So I have data and I have information. A and B, the answers to the questions A and B form my data, and this is the information generated by that data. It's a huge information. So I just want data and create information starting with this data. Okay? That's why those sigma algebras are important, and that's why now we're going to introduce a concept called generated sigma algebra. So we're going to start with an arbitrary collection of events and ask the question, hey, what's the smallest sigma algebra that contains all these events in my data list? Okay? So, question. Let A be a non-empty collection. This is the script A, okay? It's a collection of subsets of omega. What is the smallest sigma algebra that contains all the sets in A? Let me say that contains A for short. Okay? First of all, does such a small sigma algebra exist? And the answer should be yes. And the answer will be provided by the following proposition. Okay. The intersection of an arbitrary collection of sigma algebras on omega is a sigma algebra on omega. So give me some sigma algebras, intersect them, it's a sigma algebra. And you don't have to have countably many sigma algebras. You can have arbitrarily many, uncountably many sigma algebras. That's fine. Okay? So here's the formal version. Let me first state it formally. So let I be an index set, countable or uncountable, we don't care, and Fi a sigma algebra on omega for each I in this index set. So this index set is the set. I'm indexing those sigma algebras. So it could be the real numbers, it could be Rn, it could be anything, any set. So set F, which is the intersection of all sigma algebras. And now this is a sigma algebra. Let's show it. Let's show F is a sigma algebra. Well, we have to go through the definition. We have to go through the definition. Omega is in F. Why? Omega is in F because, not the empty set, omega. Omega is in Fi for each I, since Fi is a sigma algebra. So I want to show that omega is in F, and F is an intersection. So if a point is an element of an intersection, this means what? It is the element of everything in this intersection. So if I intersect sigma algebras and want to show that omega is an element of the intersection, I have to show that omega is an element of every set in the intersection. And that's what we do. Omega is a set, is an element of Fi for every I. Therefore, it is an element of their intersection. Well, let's check the complements property. Let A be in F. And now we use it. This means what? So A is in Fi for each I. What does that mean? Well, I have to pass the complements somehow. Therefore, a complement, so by 2 of definition, a complement is in Fi for each I. Well, if a complement is in Fi for every I, this means a complement is in the intersection of all Fi's. So a complement is in the intersection of all Fi's, which is just F. The index set does not really matter. I'm not using any properties of the index set. It's just there to define a collection of sigma algebras. And finally, number 3, let A1, A2, etc. countably many, don't stop at a finite number, countably many sets in F. I'd like to show that their union of A1, A2, etc. is in F. So let me first use the fact that each thing is in F. So A1, A2, etc. is in Fi for every I. So since each Fi is a sigma algebra, let me use a different index. Let's not use AI here because I is for F's, not for A's. Okay, be careful here. Don't confuse the indexes. So this is in Fi for every I. Well, now I have something that is in Fi for every I. This means this something is an element of intersection of Fi's. Which is F. And that's it. So F is a sigma algebra. So that's a nice little result. If you have some sigma algebras and you happen to intersect them, it's a sigma algebra. That's it. It has a nice consequence for us. First of all, any questions, please ask. You're always welcome to interrupt during proofs, during statements, okay? Just ask your questions at any time you want. Any questions? Okay. So this has a consequence for us. Remember our aim. If we start with an arbitrary collection of sets, can we find a sigma algebra that is larger than this collection, but it's still a sigma algebra? So A is not a sigma algebra, but we're looking for a cover, kind of a cover, which is a sigma algebra for A. Okay? That's what we want. Well, if I have A, which is just an arbitrary collection of events, at least I have my power set, right? Which is a sigma algebra containing A. And maybe I have other sigma algebras containing A. So what can I do? What can I do with all those sigma algebras that contain A? if I'm looking for the smallest such sigma algebra? Just intersect them, right? You're going to get another sigma algebra. And this is going to be the smallest sigma algebra because by definition, it is the intersection of all those sigma algebras. So the intersection is always the smallest set, right? If you have a bunch of sigma algebras and their intersection is a sigma algebra, that is the smallest such sigma algebra. So given an arbitrary collection A of subsets of omega, the intersection of all sigma algebras containing A is the smallest sigma algebra containing A. This is called the sigma algebra generated by A, denoted sigma A. So let me write it down in a formal way. So just take a sigma algebra. So F is a sigma algebra. And make sure A is a subcollection of F. And we are sure that this is not a stupid expression. The intersection is not non-empty. There is at least one such sigma algebra. At least we have 2 to power omega, the discrete sigma algebra, which for sure includes A, because it's the largest sigma algebra that you can have. And our interpretation for this is that A is data, list of questions whose answers are directly provided after the experiment is performed, right? And then you can answer apparently a lot more than the questions in A. And these are the questions in sigma A. Information generated by the data. Meaning that list of questions, list of additional questions you can answer if you know the answers to the questions in A. I want to go back to my example here. Okay, I'm going to add some more stuff on this example. So let's say omega is the sample space in the die example, the faces of the die, 1, 2, 3, 4, 5, 6. A is the event that it is a prime number. The outcome is a prime number. And B is the event that it's an odd number. My collection is A and B. This is my data. Okay? Somebody did the random experiment, but all you know is if your outcome is a prime and if your outcome is an odd number. Okay? You can only ask those two questions. And our claim is that this is not all. You can answer 14 more questions. Because this F here that we generated is the sigma algebra generated by A and B. Okay? So this is nothing happens. This is something happens. These are stupid questions. Let's pass them. So that's the first meaningful question, but this is already coming from data directly, right? So let's also pass it. So is it not a prime? Okay, is it not a prime? Well, I can answer this. If I know that my outcome is a prime, I can tell you that it's not a prime. Same for B and B complement. So if you know if your outcome is prime, if you know if your outcome is odd, you can tell me if it's prime or odd. So prime or odd. So A complement intersection B complement. Non-prime and even. You can tell it. People don't have to tell you that, hey, you can also answer all those other questions. You come up with those questions yourself. Okay? Because you generate this information starting with the data. That's the power of generated sigma algebras. Let's do one more thing. Well, these are just too much. Let's do maybe A and A intersection B complement. So prime and even. Prime and even. You know if it's prime. You know if it's odd. So you also know if it's prime and even or not. Can we know if the outcome is 4? No, we exactly want you to be able to say if it's 4 or not. You cannot, right? Maybe you can say if it's one of 4 and 6, right? 4 and 6 is one of those events. But 4 as a singleton is not a set in the sigma algebra. It's not generated by the information of being prime and being odd. Okay? So it's not the whole power set. It's less than that. Okay? Let's stop at this point and give a 10-minute break.